I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Okay, here we go. Our first speaker is Stanford neuroscientist Douglas Miller on Why Can't I Remember? Before coming to Stanford, Douglas earned a bachelor's degree in psychology at UC Davis. He is now a fourth-year grad student in the memory lab of Professor Anthony Wagner. Professor Wagner himself is a former Wonderfest speaker. Douglas uses three distinct methods to explore how attention affects memory. Those methods are neuroimaging, electrophysiology, which perhaps he'll explain tonight, and direct observation of behavior. Please welcome Stanford neuroscientist and Wonderfest Science Envoy, Douglas Miller.
All right, thank you so much. Let me go ahead and share my slides. Thank you, Tucker, for that wonderful introduction. Yes, I am a PhD student at Stanford, and I'm really excited to come and talk to you about memory. Memory is something that is so fundamental and just always present in our lives. Everything we do is influenced by our memory. It's so exciting, yet there's so much about it that we still don't understand. We're still pulling back the layers, understanding what really causes memory episodes to fail, what makes memory strong. And some of my work that I'll be talking about today is really trying to get at one aspect of how attention really plays a critical role in memory. So I would like to start with this quote. This is a quote by an American author and Nobel laureate, Ali Weissel. He says, "Without memory, there is no culture. Without memory, there would be no civilization, no society, and no future." And this really gets at the impact. Just learning in your daily lives, being able to use that memory and access it, but also pass it down to future generations is something that is very critical and has been really a linchpin in the creation of our society. And yet there's still so much that has yet to be discovered. One other quote that I really liked by a also former Stanford PhD student and now a professor at Cornell University, he says, "Memory is the means by which we draw on our past experiences in order to use this information in the present." And I really like this quote because it really speaks about the agency of memory and that we're actively using memory and our access and our utilization. We drive memory in many ways that we don't realize. So I really found this really a critical, a good question or a good quote. As Tucker has kind of suggested, we look at memory through a variety of different means. We have computer tasks where we design very constrained psychological experimental tasks in order to assay specific aspects of memory. And I'll get into one of these tasks and what we're trying to get at. Biological measures, sometimes heartbeat, skin conductance. We'll talk about eye tracking today as a way at getting at various measures of attention, context that affect memory, and directly the brain signals. The brain is such a wonder of, it just processes everything you are and experience and perceive and think and do comes from the brain. And there's so much of this complex puzzle we've yet to really solve. And tapping into this as a resource to understand memory is just so fascinating to me. So before we start really digging in, we have to understand, what do I mean when I say memory? Memory is a process that has four clear stages. First, how we acquire knowledge, the acquisition of memory and what factors can play a role. Secondly, how we store that knowledge. This can involve, say, the neurons within the brain and how specific neurons are feature specific to certain items, or how the ensemble of neurons really play a role. We can talk about the retention of memory, How is this memory stored long term? Is there any updating principles? Do we see it shift from brain region to brain region? And lastly, memory retrieval. How do we access the previously stored knowledge to solve problems that are current and that we need to solve? And in my research, I specifically focus in on the acquire and the retrieval side of memory. I'm really fascinated on kind of the underlying mechanisms that build up a strong memory representation, and likewise that could, slight echo, that could disrupt memory retrieval. Now, memory is actually quite complex. And when I say memory, I could be talking about many things. So let me break it down a little bit. So memory can be split into two general categories. You have short-term memory, also known as working memory. And this is the memory that you kind of manipulate into your mind. If I was to tell you to imagine holding a newspaper within your hands and reading through the sentences and turning the page, that is a form of memory, holding the representation of what is a newspaper and the action of turning in your mind. Long-term memory is more things you've experienced in the past that influence you. And we'll get into a lot more specifics, as long-term memory can be further broken down into explicit and implicit. Explicit memory being stuff that you have access to. When I say retrieve a zebra into your mind, what does a zebra look like? You can actively do that, versus implicit memory, which it still influences you, but might be harder. And a great example of implicit memory is motor memory. If you're typing on a keyboard, or anyone who's played a musical instrument, you'll find that sometimes you can't really bring up the idea of what it means to really do this action, but you have this motor memory built in that allows you to perform this quickly and accurately. And lastly, explicit memory can be further broken down into episodic and semantic memory. Episodic memory are events that particularly happen to you. For instance, if I asked you where you grew up, or perhaps what you ate for breakfast, these would be examples of episodic memory. They're rich in detail and very vivid, and you can almost place yourself back into that memory. As opposed to semantic memory, which is really interesting. It's memory and knowledge without a real source. And so if I asked you, what are the colors of a bee? You can picture it very clearly and say yellow and black, but you might not know where that source comes from. You've kind of stripped away some of the location and context of these features to study semantic memory. And so you can see, when I say memory, what aspect of memory can really influence what I'm studying. And so I'm going to focus in specifically on episodic memory, these memories that are really personal and you can vividly recall. So what makes a memory? Not all memories are equal. Some memory, for instance, when I ask you, well, what did you eat for breakfast, can be easy to recall. Oh, I had pancakes. If I ask you something like, 3 weeks ago when having a conversation with your neighbor, what was the first thing he mentioned to you? Now, this might be very difficult. And there are a number of factors that could play into whether a memory was either encoded very strongly or retrieved very strongly. And I'm very interested in what separates a strong memory from a weak memory. So in order to kind of get at one of these fundamental mechanisms, I'm going to have you all participate. And so what I'm going to have you do, there's not going to be a test afterwards, so no worries. I'm going to have you focus on a star, and I want you to focus on it as intently and as long as possible. It's actually kind of hard to focus in on one object. You might notice your eyes kind of bouncing to the various corners or kind of moving around. Focusing in on one non-changing thing is actually quite difficult. And this is something we call sustained attention. And what's very interesting is it kind of waxes and wanes and moves around, and it can influence things like when a distractor comes into your focus, how likely you are to break focus and have your attention shift. And so almost like a candle that is flickering, your attention is constantly waning in and out of focus, even when there's nothing kind of pulling at your attention or distracting you. And I'm very focused on how these kind of very minor changes of attention can affect memory. Because if even in the example of seeing the star, if there's these changes in memory process through this minor effect, well, then there's a lot of consequences to understanding that and interpretation of what does it mean to not remember something. So another example, we're going to go through a short story. And I'm going to have two characters in the story. We're going to call them Brendan and Brandon. They're both going through their day, maybe going off to work, and they come home, and Brendan wants to talk about the story. He says, wow, I saw so many dogs at work. I've never seen so many dogs in my life. I saw a Shih Tzu, I saw a Doberman, there was a Great Dane, there was and on and on and on. And even though Brenda's really invested, she likes dogs, this, just like that candle flickering, her attention can also flicker and wane. And so in a precise moment when Brendan says, you know, I've always liked that breed. What do you think we should about adopting this breed? This is where the critical moment happens when you're like, oh no, what was he saying? I kind of lost it for a second. Was he talking about a Corgi or maybe a Great Dane? These are going to have drastically different life experiences going on. And so it's actually really critical to kind of understand how these moment-to-moment lapses of attention can lead to real consequences due to having a memory failure. Luckily in life, we have the ability to just ask again. And this is something that I encourage at the end of the talk. If you want to go back and be like, you know what, I was lapsing in attention in this part. Do you mind going over this? I'm very excited to do that. But one of the things we can do is try to get at, well, what is the brain doing? We can talk to people, but a lot of times, especially with attentional lapsing, you don't encode memories very strongly. So if I ask you, well, what happened there? Well, you didn't encode anything. So it's really hard to actually get at. And so one of the things we'll do is study the brain itself. And so one of the ways that we study is with an electroencephalogram, an EEG. And this is basically putting electrodes directly on the scalp and measuring the electrical impulses that the neurons are firing, getting what the brain is doing. And the beauty of this technique is it's almost real time. If they see an object, you can see it within the brain waves right away. And so that's an amazing ability to really focus in on when combined with experimental design, specific aspects of memory and decision making. However, the downside with this is that because these electrical impulses are kind of going through the scalp, going through the skull, you don't really know where the brain, the source is coming from. Is it really kind of, you can say like, oh, it's in a frontal area, but you can't really say like, oh, it's in, say, the hippocampus or in the visual cortex. And so we move on to our second technique. And so we have fMRI. fMRI uses magnets to kind of measure the blood oxygen level. As you start to use the brain, you burn off oxygen, and so the brain sends blood to that area, and we can measure this, kind of lights up, and this gives us really precise measures of the areas of the brain that are lighting up. And so we can learn things about, oh, well, if you have to direct attention, what area is really responsible for that? Do you see a measure decrease when attention also decreases? These are the kinds of questions you can ask with MRI. However, the downside to this, in contrast to EEG, is that it's not very fast. It takes a while for the blood to move to the area, so you have a couple of seconds delay that you trade off for this specific location. The other downside of these two techniques is they're not very practical. There's not a lot of opportunity for people to walk around with electrodes on their head or to go into a giant fMRI to do a behavioral task. And so we have a third technique, which is pupilometry. And we've learned that through eye tracking, we can measure the dilation of your pupil And this is actually a pretty good metric of attention. And so I'm going to be using this as well for future research. I feel like it's a very low cost way of studying attention and its effects on memory. And so now I'm going to go into, well, what are we doing when we're studying this? And so this is a recent paper from 2020 with one of my colleagues. And this is the kind of work I'm doing, where they're setting in a EEG. They have electrodes, we're measuring pupils, and they see a fixation cross for 4 seconds. And now I talked about how memory and intention is really important. So now we're going to give them a specific goal to focus on. We're either going to tell them to make a pleasant or unpleasant judgment, some characteristic of the item, or a bigger or smaller judgment. Is the item big on the screen or small on the screen? This perceptual judgment. There'll be a small delay, and then they'll get the object, and they're just making a left or right key press. But what's important is we are interested in memory encoding, and we're going to be studying this part later, but the results I'm going to show you are at memory retrieval. And so at memory retrieval, just like that star I had you focus on for a set amount of time, here we extend the fixation cross to 8 seconds. So as they're waiting for the task to go, we hope that they kind of attentional lapse and they're like lose focus a little bit to try to measure, oh, do we lose focus before reactivating your goal, your intention? Or does losing focus right before the item? How does both of these things affect memory in different ways? And so what's interesting is we will ask you, did you see this item before? And that's the last category, new item. But we also ask the intent. Were you intending to pay attention to the physical features of the item? It's pleasant, unpleasant, or the perceptual features of this bigger or smaller? And so what we find is using EEG, we look at the specific range called alpha, and this has been correlated with attention. D prime is a measure used, and I can go into more details if people need, but it's a way to dissociate actually having memory from kind of just a loose noise, like, oh, I feel like kind of, but I'm not sure. It's how psychologists in my field study memory. And what you find is that as this mean alpha power goes up, you see the memory go down. And so in other words, one of the things you can do is if you have a trial by trial measure of their alpha, you can actually predict how well they're going to remember that item later on. But like I said, this is with EEG, which is kind of clunky and hard to use. What about the pupilometry? So pupilometry is the same thing. We're measuring the pupil dilation and how much it's changing, and we see the same effect. As this increases, you see a decrease in memory. And this has a lot of interesting consequences. First, this allows us to capture attention through a metric that's really easy, very practical. This could be done through cameras on a computer. We have shown that attentional lapsing seems to be correlated with worse performance. And by that factor, we can try to implement and create new interventions that can recapture attention at moments of attentional lapsing and hopefully improve people's memory for key items when they're studying or even going out throughout their day, or say like driving in traffic. There's a lot of things that could be really useful through this technique. But where do we want to go now? What am I really interested in? Well, if you notice, there was 2 techniques that we talked about. We talked about EEG, we talked about pupilometry, but I left one out, and that was fMRI. And that's because that's our next project, is incorporating the specific areas of the brain with these kinds of attentional measures to really understand, well, what's the brain doing? As I mentioned, that Rubik's Cube complex puzzle, this Gordian knot of the brain is still really not understood very clearly. And so this is going to be another way we can get at fundamental principles, what the brain is doing and how this actually correlates to real behavior. Next, we can look at, well, we understand kind of how attention is working in younger adults, but we can look at aging adults. We know that memory kind of decays with age. But what aspects of memory? Is it an attentional focus? Is it something else? Is it goal-directed perceptual? We can really get at not only understanding general aging adults' memory, but even things like Alzheimer's disease. We can have precursors. Do we see an attentional difference between young adults as they're starting to age? Can we figure out what subjects will likely lead to Alzheimer's? These are very important questions that we're really trying to understand in our lab. And likewise, I mentioned interventions. We're working on simple things like, if you can track pupilometry with a camera and see the dilation of the pupils, could you do something like change the background color of an individual screen when they're attention lapsing? And just like that flicker I had on the bottom right corner, does it orient your attention? And so there's a lot of potential for these kinds of techniques. And I'm barely starting to tap into this field, but I feel like there's a lot of potential, not just for understanding the brain, but real world applications for students, family, employees, and also for medical. I just wanted to quickly thank my lab, Anthony Wagner, who is the PI, the person I work with closely, and he's really drawn my attention to these kind of key questions. Kevin Medor, who is the individual who you saw the data for, and he's really helped work with these kinds of questions. And yeah, in my lab. Yeah.
Great, Douglas. Thank you. I want to encourage folks, since these events are called Ask a Science Envoy, to be willing to put your hand up, perhaps, be acknowledged, and then put yourself on the webcam and unmute yourself and ask a question. Or, of course, please feel free to type a question in the chat. And then, again, you're going to have to trust me to read it accurately. I'll do my best. A quick note here from Judith, a Wonderfest regular, says that Elie Wiesel was not born in the US. I think actually Douglas said he was an American. Maybe he's changed nationalities. Has he become a US citizen, or is that, I've just missed it entirely? We'll work on that. Is that fair enough to say? Yeah. All right. We have Blame John with his hand up here and a question. Please, Mr. Blame.
Yes, hello. Blame John. I have a question. Where is it? Oh, first of all, it's just fascinating. This is really fascinating. I myself had a brain injury, very serious one, in 1973. And I'm just wondering, do you have, this is off topic, but do you have you heard anything about any advances in like bionic memory? And some way of putting something in your brain to make your memory stick better.
Yeah, so this is actually a very novel field. I haven't worked too directly in this, but I did work in intracranial research with individuals who have epilepsy, where they would put electrodes directly and try to measure activation. And you can store patterns and re-stimulate those cells to try to re-trigger memories. A lot of this, from our perspective, we don't really understand the intricacies of memory. But I do know, like, Elon Musk is really trying to pioneer this field of encoding and understanding how to save things electronically and then re-deliver it to the brain. Yeah, so it is an exciting field, but I haven't worked too closely with it.
Thank you very much. That was a good answer. Thank you.
Thanks for your question, John. Jim Stauffer, how about firing your question our way?
Yeah, I came in late, so I don't know how much was covered about intrinsic value of interest on part of the subject in what they're watching and maybe losing attention over. And specifically, people who are depressed report little interest in things that other people would find worth pursuing. And I was wondering if there was any correlation that might relate to what the work you're doing.
Yes, definitely. There's a lot of studies on motivation, and that's kind of one of the things that we're getting at is intent. Right now we have pretty simple measures of just perceptual, where we'll ask if an item is pleasant or not. I did used to, in the intracranial world, we would do a lot of like gambling tasks where we would deal with individuals who were, hospitalized for epilepsy. So they were kind of on the more depressive end. And you can see motivation and how they would start with really high motivation because it's a novel task and they're really excited and engaged. And you can just see the energy level kind of drop off. That's not the same as like an ordinary or neurotypical individual. So yes, motivation plays a huge role in these kinds of features. What's interesting for us is if we can understand the attentional component, and then we can understand, well, how do you modulate the intentional component? Is something like giving periodic rewards to the individual, does that reorient attention rather than just having something like, say, changing the background color of the screen? But
I was also wondering about the diagnostic potential, in diagnosing different kinds of depression, that kind of thing.
Yeah, depression is a really complex topic. So I don't think you'd be able to diagnose from simply looking at measures of attention. But if you combine it with things like how they respond to reward, I think you would get a better measure of depression, or even like manic for people who are manic depressive or bipolar. Yeah.
Thanks.
Thanks for your question, Jim. I see Gary has a question. Please, Gary, go ahead and ask it yourself.
Yeah, thank you. I guess in the spirit of, I guess there's an upcoming presentation on algorithmic manipulation. Could your research lead to a podcast or news content where you triggered attention via some mechanism and then get and manipulate what people take away, even though you present maybe an unbiased, complete analysis of a problem, but because you direct attention to certain things by manipulating the background, like you said, that people come away with manipulated perception.
Yeah, I mean, the classic example of this is magicians. Magicians are known for kind of forcibly tricking you to reorient your attention so that way you don't notice what's going on inside. And yes, most researchers have to be really careful about what they study for it being used for both moral and immoral reasons. So if my research really understands like, okay, attention is a critical component and here's how you keep someone actively engaged, baking in some formation of like, well, this could be used for, say, marketing, but marketing is not necessarily bad. You could also be using it to market
my screen just cracked.
Sorry, I'll mute that.
But you can use it to market, say, if you're trying to get people's attention for a drug that could be helping a specific disorder, learning how to recapture attention at the moment before that, so that way more people can remember and more eyes are drawn to that, I think could be very useful.
Yeah, it could be useful, but also like a fox get and say, well, we're, getting people all worked up over a specific topic, and they could have an algorithm that figures out how to even amplify it more.
Yeah, I will say it would, even if you have an algorithm like this, it would make the memory of that event stronger. But your own bias, there's a lot of other factors at play. So yes, you would remember it, but do you believe it is a different story.
Okay, thank you.
Yeah.
Thanks, Gary. Douglas, maybe I can squeeze a question in here. You've talked about pupilometry. I wonder what feature of the pupil, anything other than diameter, that is the size of the opening, that you're measuring that reveals something about attention and memory?
Yeah, so there's a lot of work with eye tracking, especially when you retrieve old memories. You find that the patterns that eyes move kind of repeat the same patterns you moved previously to the item. And so if you have, say, somebody staring at a computer screen for extended periods of time, and they are re-exposed to the same events, you can see the same kind of patterns, and that would actually get at memory. But these are kind of new techniques. So there's not a lot that we have like a wealth of database for this yet.
Yeah.
But yeah.
Thanks. I see Catherine, you have a question. I take it you've got it in the chat here. If you'd like to ask it yourself, please do. Otherwise, I'll read it. All
I'm
right,
okay
Catherine.
with you reading it. Thank you.
Great. Does anyone find different attention profiles for those with ADD who have hyperfocus, or is that not measurable using the tools you mention or look at?
That's really interesting. So the work that I'm specifically looking at is kind of these moment-to-moment attentional changes that are very quick scale. So those wouldn't be susceptible to the same thing as like ADD. So with ADD, what happens, it's not completely my research, so forgive me if it's kind of just in the ballpark instead of like a true report. But what happens is you tend to overfixate on everything. And so whenever a distractor comes, you kind of focus on that. And so what happens and what people report is, well, I can't focus on things, but it's less that you are unable to focus, but it's you're focusing on everything. And so you're not really filtering out the kind of unnecessary noise in the environment. And so the kind of work that I'm doing, because it's on such like a micro scale, these kind of moment to moment, you don't even realize you attentional lapse. It doesn't kind of play into the same mechanisms that like ADD or ADHD would really play into.
Interesting. Thank you very much.
Yeah.
Catherine, thank you for your question. Yeah, it's probably time to move on to our second presentation. We'll have a chance to thank Douglas and our second presenter at the end of the entire program. So by the way, prepare yourself for the American Sign Language silent applause, if you like. Now, our second speaker, UC Berkeley astrophysicist Sergiy Vasylyev, will help us explore cosmic fireworks. Before coming to Cal, Sergiy earned a Bachelor of Science degree in physics at UC Santa Barbara. He is now a third-year grad student working with legendary astronomer and Wonderfest board member, Alex Filipenko. He's working on supernovas and other compact cosmic objects that go boom in the night, perhaps with no noise, but they are explosive. Sergiy originally comes from Ukraine, from which he moved to the US with his family to seek better opportunities. Who of us doesn't identify with that family history? Please welcome UC Berkeley astrophysicist and Wonderfest Science Envoy, Sergiy Vasylyev.
Thank you, Tucker, for that introduction. Go ahead and get this started. All right. And of course, thank you to Douglas for that wonderful talk. It was truly unforgettable. I had another joke planned, but my memory escapes me. All right, okay, I promise I'm done with those. And now for something completely different, cosmic fireworks. For this talk, I will have us leave our terrestrial laboratory and look out into the stars in pursuit of discovery. I called this talk Cosmic Fireworks because we'll be looking at the most spectacular explosions in the universe, ones from which we can test our fundamental theories of physics and cosmology. And no, we're not talking about beautifying the hair, nails, and skin. That would be cosmetology. But before we make that hyper jump into space, let's look at some of the largest man-made explosions. Here is the Guinness World Record biggest firework ever made. There it goes. And of course, this isn't even close to the time and money that's been spent on developing weapons of mass destruction. Take, for example, the Castle Bravo nuclear test, which was about 15 million tons or 15 megatons of TNT. Or, for example, the Tsar Bomba, the most powerful nuclear bomb ever detonated on Earth. And that was about 50 megatons of TNT. All of this pales in comparison to what we will talk about next. What you are seeing here is an animation of a cosmic firework, colloquially known as a supernova, a dying star giving one last hurrah before releasing energy equivalent to 10 to the 28 megatons of TNT. That is a 1 followed by 28 zeros. The most powerful nuclear bombs don't even break 100. And these explosions are truly beautiful. Here's a real image of the Crab Nebula, a massive remnant of an exploding star. It went off in the night sky in 1054 AD, and it appeared as a new star in the eyes of curious stargazers. Here's another one of my favorites, Tycho's supernova remnant, named after Tycho Brahe, a Danish astronomer who observed it in 1572, and he also called this a new star. But these stars are hardly new. In fact, they are stars at the end of their lives, giving off as much energy in 1 second as the sun will in its entire life. We are only beginning to understand the nature of these explosions today. For example, we have figured out that supernovae explode differently depending on the star and its surrounding environment. The explosion responsible for the Crab Nebula likely came from a star that ran out of fuel, collapsed in on itself, then it rebounded. We call this a core collapse supernova. On the other hand, Tycho's supernova likely came from an exploding white dwarf, the leftover core of a bloated star. It steals mass off of its partner until it ignites and rips itself apart in a runaway nuclear reaction. This is a so-called type 1a supernova. So far, I've only shown you animations or real images of very old supernovae. Although old supernovae bear useful information, it is the young supernovae that give us a direct window into the physics of the explosion. Here's the supernova 2011 FE, a type 1a in a nearby galaxy. You might have a hard time seeing it, so let me help you out. There you go. But can anyone tell me if this is an isolated, single, massive exploding star or an exploding white dwarf that's in a binary system? I can try zooming in, but it won't help you. Why? It's because objects very far away look very, very small. We do not have the technology to resolve these explosions. So how in the world do we know what's going on? Am I making all of this up? The short answer is no. I'm not making this up because nature has given us a way to study objects billions of light years away from the comfort of our Earth. And we do this with light. Light is our supreme informant, both a wave and a particle, a messenger carrying information in the form of changing electric and magnetic fields. This is why we call it electromagnetic radiation. When light is treated like a particle or a packet of energy, it is called a photon. And these changing electric and magnetic fields can be produced by simply jiggling an atom back and forth. Luckily for us, any material that is above absolute zero or 0 Kelvin will have its atoms in motion, jiggling, releasing light. The hotter the material, the bluer the glow. The cooler the material, the redder the glow. Just like you see here with the metal rod. And bluer light has a shorter wavelength and higher energy compared to red light. But there is another gift from nature, And that is the way that light interacts with atoms. Take, for example, this hydrogen atom, the most basic neutrally charged atom there is. One proton, one electron. The electron can occupy different energy levels in an atom. And if an electron can absorb a photon or light, it will climb to a higher energy level. If an electron drops to a lower energy level, it releases a photon. So energy is always conserved. So let's take a look at a hydrogen atom simulator to see how this works. All right, so here you should be seeing a hydrogen atom simulator where I'm showing a proton and electron in red and electron in green here, P and E. What I'm going to do is fire a photon at this atom. I'm going to fire a random red photon, low energy one, and nothing happens. What if I try to give that electron a more energetic photon, maybe blue-green? Still nothing happens. All right, what if I crank that up even higher? Let's make it UV. This is a very high energy photon. Nothing's happening. But now what happens if I give it a very specific wavelength? Now it moves. And we see this pattern for other energies that it can jump. So for example, we can jump from the lowest energy state to the third. And the energy supplied by the photon was exactly the amount needed to go from point A to point B. So you see here that there are very discrete energies that are acceptable for these transitions. And you see that when that electron drops back down, it releases those photons. So now what happens if we give it a photon that has so much energy that it completely overwhelms the energy that's holding both the proton and electron together? Boom, you knock off the electron. And that is called ionization. So you can have atoms move between energy levels or completely leave its parent atom, the proton here, and become free. So we just saw how a hydrogen atom has very specific wavelengths that it can either absorb or emit. But because different atoms have different levels that electrons can jump to, this means that every single atom has a unique fingerprint. That means I don't have to fly all the way out to the sun, for example, scoop up some gas, fly it back to Earth, and figure out what it's made out of. And we can apply this concept to not just the sun, but also supernovae. Let's look at a supernova spectrum, for example. By looking at light of different wavelengths or colors, we can figure out what elements are formed without having to fly all the way out to the supernova, which could be as far as 1 billion light years away. Using these techniques, we have learned that supernovae occur roughly once per 50 years in a typical galaxy like ours. They are 10 billion times more powerful than the sun. And they produce the heavy elements that we are made of. So the iron in your blood and the calcium in your bones probably came from a supernova. We have found many different types of supernovae, likely coming from different stars and environments. And supernovae also tell us that our universe is accelerating in its expansion. And there are still many ongoing problems in this field of astrophysics. And this is great for me because otherwise I'd be out of a job. There are many problems from which I can pick, but today we will focus on a small part of the very first question. What is the geometry of supernovae? What is their structure? To do this, we will have to get a bit technical here. And this is where I say, welcome to spectropolarimetry, or counting polarized photons or light from supernovae. Okay, so I'm throwing jargon out here. So what does polarized mean? Maybe it sounds familiar, and that's probably because you use things that are polarized. For example, if you've ever used a computer monitor, which I'm sure you are now, or sunglasses, hopefully not now, you're looking at strongly polarized light. Remember that light is just a combination of changing electric fields and magnetic fields. Here they are indicated by E and B. So let's only look at one of those components. Let's just look at the way the electric field is changing. So imagine light is heading directly towards your eye. The electric field might be going up and down vertically. It could be going left and right horizontally, or it can be anything between horizontal or vertical. The sun actually emits unpolarized light, meaning that the electric fields are changing in all different kinds of directions. If you look at a reflection of the sun, let's say over water or really anything shiny, you only see horizontal electric fields. These are the only ones that are not absorbed by the surface. There's physics that goes into here that I will not explain, but all this is saying is that reflections are polarized. The electric fields have a preferential direction. Here is where the trick with sunglasses comes in. You see, the sun's reflections are only made up of light with electric fields changing horizontally, so left and right. Our sunglasses only let light through that has electric fields changing vertically up and down, blocking these blinding horizontal reflections. So sunglasses are polarized vertically. And the screen you're probably looking at right now is polarized vertically as well. I should be able to see the screen with my sunglasses because they are polarized in the same direction. But if I rotate my sunglasses 90 degrees, I should not let any light from the screen through. And what I want to show you here is that I'm not making this up, and I'm going to show you this with actual sunglasses. So let me go ahead and change the camera here. Let's see. Right, I'm going to have to take this here. We're going to set background to none. There we go. Okay, so you should see polarization is cool right there. Okay, so if I put the sunglasses like that, you see that very clearly. Now let's rotate it 90 degrees. Oh, wow. What do you know? Physics is correct. So this is pretty cool, and I think a trick you could show to your friends after this as well. What's interesting is that my monitor that I'm giving the presentation from has its polarization is horizontal, so I actually can't see the screen with sunglasses on. Okay, let's see. All right, back to my planetary nebula. There we go. Okay. All right. So now with all of this out of the way, the technical background, let's imagine a supernova that is spherically symmetric. There is no preferential direction for the electric field, is all I'm saying here. There are as many electric fields in the vertical direction as there are in the horizontal. So those blue lines are only corresponding to electric fields. In this case, the supernova is unpolarized. But what if the supernova was instead an oblate ellipse? Something like this. In this case, we see that there are more electric fields in the vertical directions than there are in the horizontal. This supernova would be polarized. What if there was instead something blocking the light from one part of the supernova? Here we see that there is a preference in the horizontal direction. This is also polarized. When we look at young supernovae, however, we can only see the light coming from the outer cooler layers. And as the explosion expands and cools, we see deeper and deeper within. This is because the inner layers, inside the inner layers, it is so hot that the gas is actually made up of free electrons. These electrons were the ones that were kicked off their parent atom. The photons will bounce off of these free electrons, and this will happen over and over again. So the photon doesn't have a way to get out of the hot gas easily. But in the cooler layers on the outside, the electrons don't have enough energy to be free. So they go back to their parent atom. And the proton keeps the electron hidden away for most of the photons. So they don't bounce against the electrons and they fly by easily. Okay, so now let's imagine a slightly more complicated scenario. We're going to imagine a supernova with a spherical outer layer and a non-spherical inner core. The blue shell that you see is cooler gas where the electrons are with their protons. So they light through pretty easily. And the red region, that instead contains the very hot gas and free electrons that are basically blocking the light from escaping easily. So we can't see anything in the red region. It's opaque to us. At first, we are only able to see the outside, the unpolarized spherical shell. But as time goes on, the supernova expands and cools. The red region of the very hot gas recedes inwards. So we see deeper and deeper layers until we get to the non-spherical core. As the core emerges, the light with electric fields in the vertical direction here become preferred, meaning that it becomes polarized. When beforehand, we only saw the light from the shell that was unpolarized. So this is actually the same mechanism used to explain the data seen here for a core collapse supernova. You can see on the x-axis here, days since explosion. 0 is the time when the explosion goes off. And on the y-axis, you get increasing polarization. So the higher up you go, the higher the polarization. And what do we see here? The polarization is almost 0 at around 40, 60, and 70 days after explosion. And then suddenly, it shoots up to over 0.5% at 100 days after explosion. And guess what? This is when the core emerges. We have seen this behavior over and over again. And it appears that core collapse supernovae have non-spherical cores. We believe that these asymmetries are actually caused by powerful jets of material during the explosion. However, we are not actually sure how these jets are created. This is only one piece of the puzzle that are supernovae. These are the fireworks that light up the universe, the factories for heavy elements that make up you and me. I will leave you today with this beautiful collage of supernovae to hopefully convince you that they are truly worth our time. Thank you.
Thanks, Sergey. All right. I'm going to ask you a question just while we wait. I hope to see a hand or two raised. You mentioned non-spherical cores of certain stars, supernovae to be. What would cause, it just seems like gravity tends to make spherical objects, whether they're planets or stars. What would cause a star to have something non-spherical inside of it?
I have a nice cop-out answer for why things tend to be spherical, and that is that gravity does seek the lowest energy. So a spherical shape is actually the lowest energy you'll be in. So in order to make this a spherical core, you saw that I was talking about the jets. They actually end up pushing out material towards the sides. So seeing these jets in the very last image that I can bring up again, you could see that these jets we actually see evidence for these jets in supernovae, which means that they probably explain why for almost every single type 2 core collapse supernova, we see weirdly aspherical cores while everything else on top is still spherical. That's because the jets break out through the center, so they push the material going out. Sometimes they can go so much through that material that they even make the outer shells aspherical. So again, the technicalities, the little tiny finer details, once you go down that road, then it becomes very complicated.
All right. Thank you, Sergey. As I was asking the question, I just began to reflect on there are non-spherical things locally here, right? The solar system is non-spherical. And I guess the sun is slightly non-spherical, even though gravity's at work. Could rotation, which is responsible for local things being non-spherical, could that be at play also that would make some supernovae non-spherical?
That's a great question. And in the case of a aspherical core, if you're having rotation and you're getting an aspherical core, but a very spherical outer envelope, that's kind of strange. Wouldn't you have a consistent shape throughout if it's the whole star is rotating? Unless you maybe have differential rotation, like the core is spinning much faster than everything else, that would make it stretch out. So, I mean, if someone wants to see this in effect, you can take like one of those, a water balloon, and then throw it up in the air and make it spin. It'll stretch out perpendicular to the axis of rotation. So that has been used to explain some possible asymmetries in just the overall shape, but stars don't spin very fast, especially these very massive ones. They don't.
Okay, thanks, Sergey. I see Jim Stauffer has a question. Please, Jim, turn on your camera and, or at least turn off your muting.
Yeah, very interesting. And I was wondering about the production of higher elements and the changes in the spectral lines. Does that happen fast enough that we can track it? Or is that a really slow process? And if you could track it, would it all take place before the visible area moved in to where you could see it?
So is the question about how quickly do these elements form in a supernova?
Yeah, is it
Okay.
years or centuries or days?
So they form in almost instantly. So when the core collapse occurs, there's so much mass being squeezed into a point that you're basically creating really fast fusion reactions. You're smashing heavier and heavier nuclei together to give you heavier things on the periodic table, which makes you go all the way up to super heavy elements like uranium, for example.
That happens, what, too fast to observe, or it's
you could see this. And another thing you could do is for products or for elements that decay very quickly, you can actually see heating from those decaying elements. So some elements do decay so fast after the explosion that you just might not have enough time to see them. But most of the elements produced in a supernova, you see them in the spectrum. It's still there. And it takes, for example, for calcium, it takes a while for that to decay. And we see that in spectra years, a year or two later down the line, if the light is bright enough. Because if it's too faint, then your detectors are just going to be too noisy to pick up anything.
Thank you.
Thanks for the question, Jim. Maybe I get to ask another one here. Sergey, sorry to pick on you this way, but I think you mentioned that blue stars, not supernovae now, just blue stars are hotter than red stars. And first I'm struck by the fact that color and temperature correspondence is the reverse of our everyday language, right? We normally say red hot, whereas maybe blue ice cold. But so that's weird. But also the temperature is something still fantastic in any case, right? A red star is still very hot. Can we see these color differences in the night sky ourselves when we look at stars?
Yes, you absolutely can. Even just going up at the night sky, look at Orion, the constellation. You'll look at Betelgeuse. It's a red supergiant. You could clearly see that it's redder than any other star. And then look at Rigel. I believe that's a blue supergiant. And that one actually appears more pale. You can't really see blue too easily. Your eyes aren't very sensitive to that. So even in one constellation, you could see a red and blue star side by side.
Cool.
And as for the flipping of colors, Oh, you should go to Alex's lectures. He always gets annoyed that it's flipped. Even some papers that we see come out, maybe not in Supernovae, but in cosmology, we've seen the colors flipped back to the popular convention, not the one we see in physics.
The Alex you're referring to is Alex Filipenko,
Filipenko.
your thesis advisor. Yeah. Jim, I see that your hand's still up. Do you have another question, or may I lower it?
Oh, you can lower it. I'll lower it. Yeah.
All right, thank you. All right, our hour is up. I appreciate, of course, our speakers, but just our audience. Thank you for being here. I like to refer to you as Wondernauts, and if you will accept that appellation, I'm grateful. I appreciate your curiosity very much. Thank you for being here. I also thank those of you who are Wonderfest donors, or even perhaps patrons, giving on a regular basis, just a little bit. It's very kind of you to do that. I want to remind you that our next event is an Ask a Science Envoy event regarding neural engagement and algorithmic manipulation. That's on Tuesday, May 17th at 8 p.m., just as you started this program here tonight at 8 p.m. All right, and now's the time. American Sign Language applause or not, please give a thunderous or silently thunderous round of applause to Douglas Miller and Sergiy Vasylyev.